The classes keep getting smaller. I mean, there's almost exactly the same number of people registered. There were 111 students yesterday. So it's not that people are dropping out, they're just like not showing up. I think the smallest class I had last term was 6 out of 72. But they had a lot of donuts to eat that day. Brought like 3 dozen. In case you're not aware, today is Tuesday, October 3rd, 2023. Usually I have to look at my phone to figure out what day it is because I can't tell. People are like, on Fridays, they go, oh, have a great weekend. I'm like, it's no different than the week. Just get up, start working, and go to sleep. Do it again. Blah, 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 logistics, yeah, nothing interesting there. This is going to change next class, but it's going to be the same here. I think Jonas said he's changing his office hours a little bit, but that'll be next week, Thursday. Just so you know, I updated that. Just so you know, next Thursday there is no class here. This Thursday there is, but next week on Thursday, the 12th, there is no class. Next week on Thursday will be a Monday class schedule. That is because yesterday was a holiday and next Monday is a holiday. And they said, we're taking an awful lot of Mondays off, so we're going to take a Thursday off for classes. So they moved the Monday classes to Thursday, just to make it really confusing. It's kind of like an out of order message sort of thing, right? So it does fit with the theme of the class. Oh, I did update this, good. So yes, your self-assessment's due on Thursday. I've had a couple of people who are asking for concessions on the self-assessment. No. If you are well enough to send me an email or open a Piazza post or message me on Discord, somebody did both, you put in more effort than it took to push the submit button. So just submit it. The goal of the self-assessments is really to help you know that you're on track or not. And if you submit it without anything in it, you either don't care, which is fine, I don't care either, or you're falling behind, in which case you're kind of acknowledging, yeah, I'm falling behind and I'm going to make this up later. Make it up later, not a problem. Did do a good job of updating these. I was like, I don't remember updating these yesterday, so I did do it. Let's talk about a failure. This one is Google. I try not to pick just on Microsoft because Microsoft's not the only cloud service that has failures. The TLDR version is they had a network connectivity engine, or a network connectivity issue. Notice the network is often the problem. Not always, but it often is. Sometimes it can be the power going out and the chillers failing. We saw that as well, right? Heat is the enemy of computers. It degraded pretty much all their services. And this lasted for, what is that, about 4 hours, 3 hours and 55 minutes. 2 normally benign misconfigurations. Oops, gosh, that never did that before. And then we did both of these bad things at the same time and the world melts down. This is the reality in which we work. In distributed systems, we assume that we're going to screw things up, that people are going to screw things up. Humans are, in fact, fallible. I know that no one in this class is fallible. I'm sure that none of you have made a mistake within the last 30 nanoseconds. Didn't want to set the bar very high, right? Half the class is sitting there going, the mistake I made was coming into class in the first place. Fine, blah, blah, blah. There's a nice little video in there I'm not going to play here. Well, I hope it's not going to play here because there's no sound. I have to turn the sound on the laptop on so it will be captured by the video stuff. But it's basically a, I used to live in New England for quite a while. And in Maine, there's a saying that you can't get there from here. And this is actually the original skit. where it's an old Maynard trying to explain to somebody how to get from point A to point B, i.e. your network configuration is wrong. It was an attempt at being funny. I'm not very good at it. Yada yada. Oh, and there's fun stuff that, of course, they tried to recover, and the recovery didn't work either. These kinds of cascading failures where one condition begets another condition, which causes something else to go wrong, and then, of course, the world comes to an end, is not uncommon. And it's not just unique to distributed systems. Almost any complex system suffers from this. When you actually read NTSB post-incident reports in airplane crashes, for example, it is often not a single failure of a single component. It is the failure of multiple components, many of which are added there for redundancy. This is the environment in which we are working. This is not web programming. When your web browser goes south, what do? You swear at it, and you kill it, and you start it again. And when's the last time you had a web browser do something dumb on you? Maybe it's been 30 nanoseconds. I don't know. But it happens all the time to me. Web pages do weird things, and my computer does strange things, and it's like I just kill things and restart them, and that's fine. But when it comes to data that we are trying to preserve, that's not an option. Nothing worse than rebooting your computer and having it say, I'm sorry, you have to reinstall your operating system. Have a nice day. No, you just guaranteed I'm not going to have a nice day. This is why you shouldn't run operating systems at all. Just simply run on bare metal. Or write your own operating system. Then you can only swear at yourself for it. Petrov, chapter 9. Much lighter reading than Petrov, chapter 14. I mean, chapter 14 is like a baseball bat up alongside of the head. What did I just get hit with? My gosh. This is worse than trying to get my friends to agree to dinner. This is trying to get my friends to agree to dinner while they're shooting at each other. That was merely in a rhetorical sort of sense, like in a game. Not in the actual reality, or not in the actual real world, because we are not in America. We are not in the US. We don't shoot at each other here. Canada is not a country full of gun nuts, only because it lives next to one. Actually, it turns out Canada has the third highest per capita gun ownership in the Western world. Number 1 is the US by far. Number 2 is Switzerland. And number 3 is Canada. What did I want you to learn? Failure detection. This was pretty simple, but it gets a little more complicated than it might have seemed on the surface. We've already talked about heartbeats. We've already talked about ping messages. That's a very basic instance of that. How do we detect failures? I kind of like the one where we turn it on our head and we say, we'll just assume everything is failing unless we hear from it otherwise. Wow. That's a very pessimistic way of looking at the world. I like it. Pessimists are seldom disappointed. And pessimism is a good philosophy in distributed systems because, as we keep saying, everything breaks. So, why is failure detection important for us? Remember, we started with the FLP theorem, and FLP basically said, hey, if you have true asynchronous operations and messages can be arbitrarily delayed, well, you're never going to be able to agree on anything with a single failure. There's no guarantee. You will be able to achieve consensus in a lot of cases, but there's no guarantee that you will always be able to achieve a consensus. Why? Well, one of the big issues here is that we don't actually have global clocks. It turns out that not agreeing on what time it is makes it much more difficult for us to reason about things like, how long am I willing to wait? What does that mean? Since we don't have a global clock, the only standard I can apply for how long I'm willing to wait is my own clock. How long am I willing to wait to hear from you? When you're trying to settle on something for dinner, there's a logical time where that ends because it's past dinner time. But, you know, if you're here in Vancouver and your friend is in, I don't know, Tehran, you got that nice 11.5-hour time difference. So your definition of dinner time and their definition of dinner time might be a little different. And if you're from Spain, then the definition of lunchtime here is the definition of dinner time in Spain, right? Restaurants don't even open till 9 o'clock. You know, it's like civilized. Lots of things that can go wrong. Nodes fail, networks partition, networks just randomly misbehave. Hey, I'm going to stuff those packets in a little corner here, and I'm going to hold them for a while, and then I'll send them out on the network. What? I'm watching the Georgia Tech class right now fight through some of the DS Labs tests on unreliable network, which reorders packets and drops things, which looks kind of the same because remember the client keeps retransmitting. They're like, well, my code works when it's a reliable network, but fails when it's an unreliable network. It's like, well, guess what? You're not handling the failure condition properly, are you? That's not going to catch you because you just spent a whole bunch of time thinking about the problem rather than trying to sit there and fix it in your code editor. It was actually pretty interesting looking through the design proposals. Most of them weren't actually, hi, how are you? Here's my syllabus for CPSC 404. Most of them were actually somewhere between, all right, I gave it kind of a little bit more than minimal effort, to a few that are actually pretty impressive. And we're working through to try and pull some of those pretty good ones out. And we'll try to highlight probably about a half dozen of them a little later in this week, poking at each of the TAs to look at them. I want to see what they think makes a good design as well. I haven't done it yet, but all of the design projects that were submitted have been uploaded to the GitHub, and I will be adding all of you to that repo. I could do it now, probably at the end of class I'll do it. And then you can actually see what everybody did. And there's like 109 of them. I think there were 111 students total in the class. And I think almost everybody submitted it. There were like 2 people. So you can see what other people did. And it runs the gamut. Some of them are really interesting. It's really cool to look and see what some people put into it. And they said, I want to understand the problem. I want to understand the failure model. And then from that, they reasoned about how can you approach this. And part of the reason I want you to look at those is because I want you to say, which of these would I want to implement? You know, this time I've said, pick one of the 3 that you were given and use it and implement it. Because that's going to give you a little more insight into what was good or bad about that particular design. I don't care about the code. Code makes no difference. The goal is for you to say, what makes a good design? And what makes a good design is it's something you can pick up and you can get more code implemented in a shorter period of time than you would have done if you hadn't had the design. So if you got 3 really crappy designs, maybe you got the CPSC 404 syllabus, the high, and the, I had 5 minutes to write this, so I've got 3 paragraphs. And you get to pick whichever one you think is best, and you can then say, well, you know, these were really lame. None of them guided me very well. That would be kind of getting dealt a bad hand. Maybe next time I should let you look at all of them and pick one, and to say, this is the one that I thought was best, and see how far you can carry it. Maybe we'll do that for design project 2. It's not too late to change that. Heartbeats and pings are a traditional way of detecting network connectivity. If I send a heartbeat message, I send a ping and you respond, I know you're still alive if I receive the response. If I don't receive a response, I have no idea what's wrong. You could be down, the network could be down, maybe you received my ping, but I'm not receiving yours because the network has decided that packets from me to you go through here, and packets from you to me go through Afghanistan via carrier pigeon. And you laugh, but in fact, asynchronous routing like that happens in the real world. I've used satellite internet where you would send messages through a dial-up connection a long time ago. and then it would send the response to a satellite. So that was a very peculiar way of getting bandwidth down, but not very good bandwidth up. At the time, the bandwidth up was about 56K. Down, you could get about 400K. Not great for gaming. Heartbeats and pings are simple and effective. It's really easy to build. So we use it because it's really easy to build. It may not be the optimal solution, but sometimes I don't need the optimal solution. But we all know as soon as we sit down to write a piece of software, we are going to write the best software ever. Yeah, no, that's not the way it works. We're going to write the software that's sufficient to get the job done. And then someone who's paying us will have us go back and make it better. Hopefully. Or you're doing it because you love it. Why would you use a timeout-free failure detector? This is an interesting case. What does a timeout-free failure detector mean? Well, sometimes we actually have problems where network latency is got a lot of jitter in it. Gee, we're talking to our Martian data center where it can be anywhere from 22 minutes to 2.5 hours to get a response. No, I think that would be one way. I think round trip would be 44 minutes to 5 hours. That's a big variation. I like using that variation because it's easy to think about. But in fact, in the real world, the difference might be sometimes it takes 20 milliseconds to get to you, and sometimes it takes 200 milliseconds to get to you. It's actually the same variation. It's even worse. 44 minutes is 0.75 hours roughly, and it's 5 hours round trip, so it's not even 10x. Whereas 20 milliseconds to 200 milliseconds is 10x. But it's easier to realize that 44 minutes versus 5 hours is quite a bit of difference. And that scale, I don't know what it's like in my head. It's easier for me to think in big numbers like that. Now when I scale it down, you're like, yeah, okay, great. So you get over that thinking that, well, I don't know, 200 milliseconds, 20 milliseconds, it doesn't matter. I can't really see it anyway. But computers can see it. Computers can observe those kinds of differences. So the reason that we wouldn't necessarily want to do that is because we have that kind of jitter. When you look at Design Lab 1, which was DS Labs 3, it uses a 25 millisecond ping timer and a 100 millisecond timeout. So in other words, in order for us to declare one timeout, you have to get at least 4 ping failures. That's great, as long as you're going to get a response in 25 milliseconds. Now, it's a simulator on your computer. It's going to take less than 25 milliseconds. It's going to take less than 100 nanoseconds. Well, maybe 250 nanoseconds. Doesn't matter. So it's not a big deal in a simulator for us to assert that kind of a condition. But in a real-world scenario, we have to understand what our network behavior is going to be like. The reason we might choose a timeout-free failure detector is because we dynamically watch to see how long it takes to get answers back, and we try to adjust appropriately. Because normally, it's not like 25 milliseconds, 25 milliseconds, 25 milliseconds, 2 days. 25 milliseconds, 25 milliseconds, 25 milliseconds, 2 days. It doesn't happen like that. Usually what will happen is you'll start to see network congestion, is you'll see that the packet's response times go up, and then they come back down. And so what you can do is you can keep track of what's the average, what's the decaying average of these things. You can be more responsive to dynamic changes in the network. That's a lot more work than building a simple heartbeat detector, isn't it? Now you're like keeping track of how long it takes and yada, yada, blah, blah, blah. If you look at the network time protocol, which is this ancient, creaky time protocol that we still use today, at one point, does anybody know XKCD? There's this really cool XKCD, which is this big-ass stack of all these open source software packages, and there's this little tiny, it looks like a Jenga, right? There's a little tiny piece in one corner that's like holding up half of the right-hand half of the stack, and there's a little pointer that says, this supported by one guy by himself for 16 years. That is NTP. That's literally what inspired that particular XKCD. And it's because this one guy basically wasn't even getting paid for it. He's doing it as a volunteer activity. And the whole internet comes crumbling down when NTP stops working. There's now an NTP foundation, actually, to support this stuff. Because it turns out that we've relied on this network time protocol for time synchronization for so long that it is a critical part of the infrastructure. We've seen the same thing in other areas. OpenSSL had the heartbleed bug, which was very infamous at the time, about, I don't know, 15 years ago or something, where they weren't scrubbing buffers. So there was like extra data that was coming along in the packets that represented somebody else's use of the same memory. Classic problem in memory allocators. So they were literally bleeding information. The problem was, of course, they were literally bleeding things like your tax records. No big deal there. You don't have any taxes yet. Software gets complicated. We rely on these things. We rely on the network time protocol, DNS, so on and so forth. A lot of complexity there. A lot of things we rely on or depend on. But at any rate, the NTP protocol uses these kinds of dynamic timing values to figure out what your actual time is. They compute approximately what the variance is between your computer and the clocks with which you are synchronizing. And you don't even think about it because everybody's computer in here, everybody's phone, everybody's watch, the smartwatch, they all do time synchronization. You can sit there and watch them. You hold them next to each other while they're all turning to the next minute, and they all do it simultaneously, what appears to be simultaneously to you, usually within about 10 milliseconds of simultaneous. One of the things that happens as you begin to increase the scale of your networks, the scale of your environments, is that this idea of, well, I'm just going to send a heartbeat message every so often doesn't scale. What happens if you have 10,000 nodes, each sending one heartbeat message to each of their companions every second? Oh, that's a lot of messages now, isn't it? Does that scale to 1 billion? No. Now all we're doing is sending nothing but ping messages on our networks. We're not actually doing anything useful with them. So we need to come up with other schemes for dealing with these kinds of environments. And one of the things we'll do is we'll outsource our heartbeats. You'll see this kind of technique used multiple times, which is rather than having everybody talk to everybody else, we percolate things up. There was a question on Discord today about one particular failure model. And the purpose behind it's the weird one where we turn it around and we assume everything's failing. Because that leads us into situations where we handle failures in smaller groups. And we only percolate failures we can't handle up. We just got done talking about consensus last week. If one of the nodes in a Paxos cluster goes down, we don't need to tell anybody. We're fine. We're going to recover from that. That server's going to come back up. Life's going to continue on. Everything's going to be great. We don't need to make the little red light go on and a siren go off and have some poor human user at the end of a pager working for Amazon wake up at 2 o'clock in the morning. Maybe some of you are night owls, so 10 o'clock in the morning. Everybody has a time they don't want to be awakened. So outsourced heartbeats are a technique where you, in essence, have intermediate nodes keep track of other nodes around them. So this reduces the number of heartbeats that we're sending around. All of the devices in your network, all your IoT devices in your home environment can talk to one of them and say, yeah, I'm alive, and it can keep track of that. I mean, effectively, my gateway, my network gateway does that, right? It keeps track of all of the devices that are on the network, and it can tell me what all devices are currently connected. Great. So for all intents and purposes, it's already implementing this. Sometimes the delay isn't in the network, it's actually in the implementation service itself, because the service can have very high high demand, high load, and it has a limited pool of resources. We see this a lot with what are called microservices. How many of you have heard of virtual machines? About half the class. The other half of the class is like, I don't know, I only do real physical machines. Sorry. How many of you have heard of containers? Docker is probably the most famous of the container models right now, but in fact it's based on a systems paper called the Library OS. The idea is that you can actually simulate living in an OS environment in a way that isolates you from everything else outside. This is what we usually refer to as microservices. They're containerized services. Sometimes they're even smaller than that, where they might be providing just a particular function in that container. And this has become a very popular model for implementing things. The challenge with them is they don't really have very much control over the resources in their environment, so their responsiveness can be highly variable. So in order for us to detect when a microservice has failed, we really need to know how long should it take for it to respond, because that's going to be dependent upon what else is going on outside of that microservice. In other words, we've got this little minion. That's what we should call them, minions as opposed to microservices. Then you have a nice mental image, right? Little yellow things. We've got these minions, and we keep them in the dark, and we don't tell them what's going on in the world, and we just give them tasks to do, and we don't know how long. They don't know what's going on, so they don't know how long it's going to take them to do it. So how do we detect failure in those kinds of conditions? And this is a model where we can build a failure detector in the outside world that can detect when a microservice has failed, because we know what to expect from it. And we know what its load is in the world in which it's operating, even though it does not have that insight. So this is another kind of failure detector. We went from simple to more complicated to, wow, this is starting to get really kind of gnarly. Gossip protocols are awesome. They're like literally where you just sort of like send messages to random other machines and say, hey, you know what's going on over here? You can actually use gossip protocols to build scalable failure detectors as well. You don't send heartbeats to everybody. You just send a message to some people saying, I'm alive. Life is good. But that's enough that we can, in general, start to figure out when things fail because nobody's heard from you in a while. This is how, UBC knows to send someone to check on your wellness, right, after the smell starts coming out of your room. I wish that were a horrible joke. It happened, but dwell on these things. This is a happy place. It's pretty cool to use something like a gossip protocol to build a failure detector, but we're definitely veering out there on the complicated kind of scale, because I just hand waved that whole thing, didn't I? I basically didn't say, this is how we're going to actually implement this so we can figure out who's failing. You have a question? That depends on the implementation, actually. So in fact, as the network itself becomes much larger, usually the number of connections that you have goes down. If you think about the Bitcoin environment, the blockchain environment, right? Everybody's talking to everybody else, but they don't talk to everybody else all at once. So in fact, they just choose 7 other random machines or 8 other random machines, I don't remember what the exact number is, and they communicate with them. And so since nobody's, well, you never lock into, you're not supposed to lock into a tight cluster. Eventually the information does propagate through the network, and that's what gossip protocols, for all intents and purposes, do. And 8 connections isn't too large that is burdensome for almost anything. That's why it works. Probably would want to make sure that your 8 connections don't form a complete cover over the 8 connections of anyone else in your immediate group. Trying to think of a good term, collective. So, you don't want to be assimilated, or you do, but don't want to be assimilated by everybody all at once, everywhere, all the time. So it's sufficient for you just to simply communicate with a few other people, and then they can figure out, over time, the network will figure out that you failed. So the other trade-off here is that it will take us longer to figure out that you have failed in any of these less dense network environments. That's fine. It probably doesn't matter. If you think about the way that Paxos works, Paxos will continue to work if a node falls off, and we'll figure it out. And if you come back, we'll figure that out too. So yeah, this isn't too bad. Hand wave, hand wave, hand wave, but that's okay. The purpose of the reading isn't necessarily to make you an expert on how to implement these things. If you decide you want to implement a gossip protocol as part of your capstone project, then you're going to be doing some extra reading, and you're going to look at how people have implemented gossip protocols. Reversing the failure detection problem. I really kind of liked this one. It was the, let's just assume nothing works. Until I hear from you, I assume you're dead. That's kind of a neat way of doing things. Instead of thinking that we have a liveness detector, we have a deadness detector. Well, no, actually, I would argue that it's the reverse, right? We detect deadness with heartbeats and pings and all these other things. But in this case, we only detect liveness. It's kind of a shift in the way we are thinking about the problem. But it has the same effect in the end. Somebody asked about this on Discord, so I gave them the ChatGPT answer. I have to tell you, I'm really impressed. Chat does a really good job of explaining these things in distributed systems. So whatever they fed her, them, whatever you want to, I tend to think of it as feminine because, of course, in Star Trek, it's always a woman's voice in the computer. They fed it a lot of distributed system stuff, all I can say. It knows all the papers and can summarize them for you. And usually it does it right. Even more impressive. And it's really good at creating wrong answers. Please give me a true or false question. No, that's the easy one. Please give me a question with one true answer and 4 plausible sounding but incorrect answers. And that's, I mean, there wasn't a lot in Chapter 9. Chapter 9 is so much lighter than Chapter 14. Chapter 14 whacked you across the head. I'm still seeing people struggling and asking questions with that. And of course, you know, right this afternoon, there was one. So that suggests to me that somebody finally got to the reading this afternoon. Did anybody read Chapter 14? How many of you felt like you understood it? Yeah, it's a lot to wrap your head around. Part of why I did it this way is we're going to come back and we're going to visit those things again. So some of this really was the moment where you go, holy heck, what did I just do? It's just, hey, get a couple of friends together and we'll make a decision. How hard could it be? The rain starts falling. Then it gets muddy. And then you can't move. That would be Burning Man, of course. Analogy there. I don't know, have any of you ever heard of Burning Man? My parents live on the other side of the mountains from Burning Man. So they live in the middle of nowhere in California, and Burning Man is in the middle of nowhere in Nevada. It's literally just on the other side of the mountains. I've driven right by it while it was going on. So it's an interesting experience. I've not been to Burning Man, but they got a lot of rain this year and a lot of mud and a lot of interesting behaviors and animals that only come out when it rains. A whole bunch of these like 300 million year old creatures that appear once in a while when it rains like crazy. Very interesting. So yeah, things go wrong. But usually they just get together and they make some decisions as a collective, as a group. And that's all that 14 was about. Well, 14 kind of presumes that we can detect failure in this I don't hear from somebody sort of way. Now, one of the things I do like about doing it in this order is now I can say, look, in 14, in Paxos, We said when any proposer thinks that the multi-paxos, when anybody thinks that the leader is dead, they can propose a new leader. And we see the same exact thing in Raft. Raft and Paxos are, by the way, the same consensus protocol. The difference isn't in how they achieve consensus. The difference is in what it means to make a decision. So I would argue that what Raft is doing is it's deciding what entry to append to the log. Remember, all we do in Paxos is we agree on a value. Well, if the value that we're agreeing upon is what goes next in my log, and everyone, meaning a quorum, agrees on what's in that particular log location, this becomes an append operation. We just agree what gets appended next. And that's exactly what Raft does. The interesting parts about Raft, and the reason that people like it, is because Raft provides a very concrete description of how you recover from the failure. Well, here's our failure detector. It's exactly what they describe. I don't know. Because I think about this, it's like, okay, so you do heartbeats and you do pings, and when somebody stops responding, stop hearing from your leader, say, I think they're dead. So you just simply stand up and say, I'll be leader. And the moment you say, I'll be leader, we have to elect a new leader. When we have a new leader, the new leader then is the one that creates the proposals. And we distinguish between the old proposals. Because remember, it's important for us to keep the ordering. How do we maintain that ordering? Well, we keep that ordering because every proposal that comes from a leader includes their ballot number. I'm this leader number. I won the election on this ballot. So the way that we hook multiple rounds of consensus together is that we keep the sequence number of one level of consensus, the leader election, and we put it in as part of the next level of decision. And in fact, when you actually look at the way people implement this, when I send a proposal out as a proposer, I send it with my proposal number, which in multi-paxos is the ballot number. We call it ballot number in Raft, I think, too. I send my ballot number, I send the client's sequence number, and the actual command. And this is kind of cool because if I get the client sequence number and the actual command, any of the servers can see if that's already been adopted anyway. Even if it was adopted under a previous ballot or a later ballot. So there's this interesting failure condition that happens because the question came up. What happens if the leader gets enough votes to accept the proposal, but dies before it sends the accepted message? I thought it was a really good question. It wasn't a question that I asked. It was a question that a student asked. And I thought it was a really good question because it was very perceptive, because it understood when I'm thinking about failure, I have to think about what could possibly fail between any two operations. And in a network, the operations are always the messages. So what could possibly fail between the last accept, or the quorum granting accept, arriving at the leader, and the leader sending out an accept message? Their question was, I don't think their question quite crystallized around this, but I realized that it was really good at understanding when you can tell the client that the proposal was accepted. The leader doesn't tell the client that the proposal was accepted. In Paxos, it's the learner that tells the client that the proposal was accepted. So here's the situation. The leader gets the final vote, dies, doesn't send an accepted message. She looks around and she says, I haven't heard from the leader for a while. I'm going to be the new leader. Sends out a new ballot for leader. Remember, now we have two levels of proposal here. We've got the leader election, we've got the actual value election, adoption. So she sends out a ballot and she says, I want to be the new leader. And people start chiming in and they say, okay, you can be the new leader. And by the way, here is the last thing I accepted. The reason we have the last thing I accepted is because this is how the new leader is going to know whether or not they're up to date. See, this is the thing. She was offline. She came back online. She looked around. She couldn't find the leader. Nobody else has actually noticed yet. They're all sitting there sleeping. Looking around at the class, half of them. And she says, I can't find the leader. I don't know where the leader is, so I'm going to propose to be leader. Or maybe she just does that out of spite. Hey, I'm new here. I'm going to be the leader. Her database, her understanding of the state of the system is behind. Raft has a very clear and very explicit description of how they restore that consistency. She can be the leader, but she can't propose things until she knows what the current state of the system is. So part of her leader election is everybody tells her what the last thing they accepted was. At least one of those will be the decision that was accepted by the previous leader. Guaranteed. Now, here's an interesting thing. If it wasn't accepted, let's say the leader had only received n-1 accept messages at n+1. So it votes for itself. So we're sitting at n. We need one more vote. We didn't get that one more vote. She comes back up. She queries. She may or may not learn about that decision. If she does not learn about that decision, it's okay. Because we hadn't actually agreed on that decision. If she does learn about that decision, it's okay because now she will be able to accept that decision. In either case, we end up with a valid state. In the case where she doesn't get that because it wasn't part of a quorum, the client will retransmit the request. She will get it. She will propose it. It will be adopted, and we will move on. If she does get it, because even though it wasn't part of the quorum, she has a quorum of the votes. So she can say, this is now adopted. It's kind of cool. And it's a very kind of hairy sort of condition. You have to sit there and you have to think through and say, if this happens, then how am I going to get back to consistency? And if that happens, how am I going to get back to consistency? But of course, this all relates to the fact that we have this, in Paxos and Raft, it's pretty simple. They're not using phi detectors or any of these sophisticated kinds of failure detectors. They're basically using a ping mechanism. It's not even really a ping mechanism. It's anybody who participates as an acceptor in this environment, or as a proposer, I guess. As anybody who participates in it as a proposer in this environment can stand for election at any point in time. But we don't have any dependency on a global clock. We don't have any dependency on anybody's clock. You could easily implement your system so that when you first come up, you put yourself up for election. I'm not sure that that's the best way to do it, but it would be a valid and legitimate model for doing it, given the way that Paxos and Raft and view stamped replication and PMMC and fast Paxos and flexible Paxos and, I don't know, Paxos made simple and Paxos made super complicated do it. The key is the ordering of events. And it sounds really simple. But the student who was struggling with the unreliable network tests in DS Labs 3, not here at Georgia Tech. They're a grad student. I think they're not as smart as this here, though. I try to explain to them, I'm like, you're not handling failure condition correctly. You are assuming, when it works, when everything shows up in the right order, that's great. It's not the interesting case. The interesting case is, what do you do when there's something that went wrong? Because the whole point of building these consensuses is so that you can handle the case where something went wrong. We are literally sitting using the simplest of all possible error detection mechanisms. I just wait until I haven't heard from the leader for a while, and then I get impatient. Now, it is interesting when you go back and you read Lamport's original Paxos paper. Well, all right, it's actually Paxos Made Simple, I believe is where he put it. I don't think it's in the original part-time parliament paper. I love the part-time parliament now. People used to talk about how really complicated it is, but I realized, having looked at all these papers, and I did this last term, and I was like, no wonder people find this confusing. You sit down, and these all use vaguely similar terminology in different ways. How to confuse people. Hey, I'll use the same concepts and give them labels that are overlapping. So you sit there and you read about Paxos and Raft and view-step replication and PMMC and blah, 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 and you're like, acceptors, learners, what are you talking about? So in Paxos Made Simple, which is the easy version of Paxos, it wasn't priests and ledgers and olive contracts. Essentially, the ledger in the part-time parliament is a log. So in the back, they make notes about what's been proposed. In the front, they make notes on what they've accepted. He was trying to divorce people from thinking about practical implementation and help them understand the algorithm. And I finally got that. I finally really understood that when I sat down and I started reading all these papers. And he was so prescient about this. He wrote the part-time parliament before people had managed to scramble all of these terms and make it really confusing for us. That doesn't make it easy. It's not easy. We are not used to thinking about what do we do when things happen out of order. But the world we live in, that really happens. When you build Kleppmann, Martin Kleppmann's class that he taught at Cambridge, and he's got some great videos online about it. And his is the other book on the list, which I said was optional and the department made mandatory. So now I'm like, maybe I'll use some of Kleppmann's readings as well. And we'll go back through some of this with Kleppmann, because I think that might help reinforce it. And it's free too. It's also an O'Reilly book, and it's part of the same exact library, and it comes complete in an audiobook version. How many people listen to the audiobook version? I was surprised. There's quite a few people who've talked about using the audiobook version. Somebody was talking about trying to read through it quickly, and I almost suggested that they just sit down and listen to the audiobook version instead. One of the TAs, whose native language isn't English, said that was really helpful. It was a lot easier to listen to the book than it was to try and read it in a really awful language. No offense to those of you who speak English as your native language, but it sucks. And we force it upon the whole world. How many of you speak English as your native language? Right. It sucks. But it's the language of travel, and it's definitely the language of the computer industry. I mean, when I was in undergrad, we had a language requirement. You had to study a foreign language. So, you'd study German or you'd study Russian, because there was quite a body of scientific literature that was published in German and Russian. Some in French too. This is Canada, so of course, but I grew up in the US, so. Some in French as well. And there's still literature in French. How many people natively speak French? See, this is how you know you're in Western Canada. One person. Bonjour, ça va? Consensus is a really simple idea that is really hard to wrap your head around, because it really requires that you stop thinking about things in linear sequential order. It's the same problem that Kleppmann talks about in his videos and his books and his conversation. His class was called Concurrent and Distributed Systems. And every single time I look at distributed systems, I look at these and I say, they look exactly like the way we build computers now. When you sit down and you look at multi-core computers have exactly this problem. They have a lot of state they have to agree upon. They have protocols where they implement shared data structures. Now, the one benefit that you have when you do a single computer is that you have a memory. But in fact, some of the systems we now build disaggregate the memory. The memory isn't in the computer. It's in a different device across the rack connected by a network. What? Yeah. Okay, so we're talking about these consensus protocols, and suddenly I'm looking at these computer architectures. We get these people who are doing research on disaggregated systems, where the CPU is separated from the GPU, which is separated from memory, which is separated from the storage. And you're like, sounds like a distributed system. Okay, that's great. And then I realized that, in fact, we've been building these kinds of systems for a long time. This is what multi-core discrete processor, multi-processor systems looked like. Multi-core systems don't look quite the same way because they share state that, that you don't see in multi-core systems. So one of the benefits of studying this particular topic is that if you decide that you don't actually ever want to deal with a network ever again, and you instead are going to deal with regular computer systems, and you're going to do concurrent programming, it's the same set of problems in slightly different clothing, but it is the same set of problems. Did anybody have questions about the failure detection models in Chapter 9? Were you relieved that Chapter 9 was such an easy read after Chapter 14? Have any of you read Chapter 9? For those of you who have not read Chapter 9, you should now feel encouraged because it will take you about 1/10 of the time that Chapter 14 did. I do like the fact that you at least had an entire weekend to go over Chapter 14. A long weekend at that, because of course none of you took the long weekend off because every day is like every other day, right? Wake up, look at what you're supposed to do that day, procrastinate and go game. No? What did you do? Instructing rock climbing. So he wasn't even, well, I guess he was physically gaming. Instructing rock climbing. You actually show them how to rock climb then? This is how you make sure you don't kill yourself. And then you watch those videos of people who do this without ropes. Like, one mistake and you're dead. Yep. You don't get the parachute that you can pull out. Doesn't work that way. Do really dangerous rock climbing like that? Not yet. Give them time. The thrill. Cool. So you didn't do any readings over the weekend because you were teaching rock climbing. Noobs. Then you were drinking. Oh yeah, I'm guessing you probably climb every day. Almost every day. Every day you can. It's an addiction. It's like gaming. How many of you actually sat around and gamed? It's almost as dangerous, isn't it? Less drinking involved. Well, maybe not. All right. Well, I don't have anything more. If you don't have any more questions. Some of the questions have been really good. There have been lots of non-questions. I usually answer Discord pretty fast. I notice that I tend to only look at Piazza once a day. So feel free to use either one. That's cool. And that's a wrap. Easy day. Not a big problem. We'll be doing Chapter 10 on Thursday. And I'll keep eating on Access and Consensus and Raft and View Stamped Replication and PMMC and yada, yada, yada. So I will be making those available on GitHub. So you'll be able to see everybody else's design projects. It should not have anybody's name in it. I didn't look at all of them, but I told people don't put your name in it if you don't want people to know who you are. If you're embarrassed by your work, don't put your name in it. If you're proud of your work, you can put your name in it. I don't care, but all the files I downloaded had names on the file name, so I wrote a Python script to compute the MD5 hash and rename them all to the MD5 hash. So that's about as random as I could possibly get. And guess what? There were no collisions in the MD5 hashes. I'm so shocked. Cool. All right, I'll see you on Thursday. Be careful out there. Consensus is dangerous. You might agree on something, or the network might fail. Yep. I'm going to stop the recording. So hold on. So stop streaming.